Good morning, everyone. Welcome to the IAA monthly seminar and Happy New Year. So it's my great pleasure to introduce Dr. Ben Zhao. So he's a Neubauer professor of computer science at U Chicago. He held the position of professor of computer science at UC Santa Barbara. He completed his PhD at UC Berkeley in 2004 and bachelor degree from Yale in 1997. He's an ACM fellow and a recipient of NSF Career Award, MIT Technology Review TR35 Award, and also Computer World Magazine's Top 40 Technology Innovation Award, IEEE ITC Early Career Award, and Google Faculty Awards. His work has been covered by many media outlets such as New York Times, Boston Globe, LA Times, Wall Street Journal, CNBC, MSNBC, New Scientist, and Slashdot has published papers intensive in security and privacy and machine learning. I still remember when I was a PhD student, I read his paper in IMCs about social network, and then recently I started reading a lot of machine learning related papers. So he's very productive, published tons of papers, and he serves as TPC co-chairs of the World Wide Web Conference in 2016 and the IMCs in 2018. He also served on the steering committee for HotNets and was general co-chairs for HotNet 2020. Without further ado, let's welcome Dr. Ben Zhao for his talk.
Thank you, Yinzi, for that nice introduction. Let me share my screen real quick. And yeah, really happy to be here. Thanks for having me. And hopefully, the stuff that I talk about will be interesting to the folks here. All right, so yeah, so I'm at University of Chicago, and I co-direct a lab with Heather Zhang, called the SAN Lab, Security, Algorithms, Networking, and Data, because we cover so much different topics in our lab. So today I'm going to talk a little bit about some of our recent work looking at adversarial robustness and how to make neural networks more robust against attackers. And particularly, we're going to talk about what is, I think, a new perspective on tackling some of these issues from the perspective of forensics. And I'll sort of talk a little bit about what that is. But before I even get into it, I think the obligatory adversarial ML slide, look, machine learning, deep learning in particular is hugely impactful. I think everyone knows. But they're also sort of known to be vulnerable to a bunch of attacks, whether it's runtime attacks, inference time adversarial examples, or poisoning attacks, where you sort of corrupt the training data for some of these models. And then there's, privacy attack on top of all that. So it's a huge community that's been really developing over the last almost 10 years, I would say. So there's big clumps of it. One big group at sort of the security perspective, the top security conferences, the big group in the core ML, looking more at sort of robustness of all different kinds, not just adversarial. And then, different projects leaking out into more specific application domain-specific places like SSP, SIGCOMM, and so on. So adversarial robustness, I want to talk about in particular is focused on scenarios where you have an active attacker. So it's not just random inputs that happen to, confuse your model and produce the wrong output. This is where active attackers are actually there and trying to do something bad and to cause errors and misclassifications and so on. So it's not natural robustness. All right. So very briefly, just sort of like a little obligatory thing. My lab, we do a bunch of different projects on different aspects of adversarial machine learning. Up top, we've shown a bunch of things looking at adversarial perturbations, adversarial attacks, and how to provide defenses against that. We've looked at poisoning attacks and defenses against that. We've looked at weaponized machine learning, when machine learning tools are in the hands of attackers and become powerful weapons. But then also finally, more recently, we've also been looking at defending privacy against invasive machine learning. So today I'm going to talk about a couple papers that are more recent, both from the last few months, focusing specifically on forensics, which I think is something that is reasonably new that I have not seen before in the security or actually the ML communities. So let me get into that. Very brief. This is the standard, I think, slide that you've probably seen like 100 times, if not more. Adversarial examples on neural networks is a thing where ever since I think 2014, from the initial Goodfellow and et al. Paper, where they show that you can take a normal classification model that looks at something like a steep stop sign, says this is a stop sign. You can tweak little pixels on top of it, largely invisible to the human eye, and yet in the feature space of the classification model, it will be completely different, and it'll classify that result as something like the speed limit. So that's a sort of a runtime attack. And over time, these sort of attacks have gotten increasingly more powerful, but they all really just rely on the same sort of gradient optimization search. If you know what the model looks like, then you can find corner cases where for any specific input, you can find a corner case where it looks like the model to be something else, right? And people have sort of, accepted the fact that these things are possible largely as a fundamental property of real neural networks, and the fact that you can have perfect training data sets. So what is interesting that I want to point out is the fact that this progression, ever since the initial FGSM paper in 2014, has been back and forth. And so we've seen literally, every year or two, and increasingly so now, it's not even a year, it's literally months before, when the defense is proposed, something almost comes back immediately and breaks it. And, I only go up to 2019, but even in the last few years, basically anytime a defense comes out, someone targets it and can show that, within a few months that there are ways of overcoming that defense. So why do I show this? This is constant back and forth, and there's no real effective known defense, right? So, I mean, with the caveats of adversarial training and certified robustness, having some robustness properties that are nice, but they both have real significant caveats that prevent them from being sort of used in most real systems and settings. Okay, so so what do we make of this? Well, you have this cat and mouse game that really seems sort of never ending. And so more recently in the security community in particular, folks have been wondering, are we sort of stuck? Are we making forward progress? Are we doing things that are still interesting, or are we just running back in circles and proposing something new, and then breaking it and then repeat? And it does seem like a perfect defense for adversarial attacks from machine learning models seems really impossibly difficult, because in some sense there is a built-in asymmetry, right? So when you have someone takes some time, create a defense, but the challenge for that defense is really the bar for that defense is really, really high, because once you propose that defense, really it has to withstand the length of time, right? It's going to be out there, and attackers can basically look at it, break it apart, reverse engineer it, and eventually come up with the defense. So that built-in asymmetry is, in some case, in a way, leading to this sort of back and forth. And so, one pragmatic question is, well, what do you do? What do you do to help practitioners who don't want to deal with this cat and mouse and say, yeah, I can deploy the latest defense with engineering and whatnot, only to have it be completely useless and broken apart in a few months? So that's sort of a fundamental question I think a lot of people are asking the community now. And one sort of take on this, my own personal take on this, is that we can look at perhaps, us reaching a plateau in sort of this current threat model that the community has been working on. And one way to move forward is to think about expanding that threat model to something that is closer to what practitioners deal with and in real systems. So what do I mean by that? Well, one thing that we consider is what I think of as currently this binary view of robustness. In other words, you have a defense, okay, and you design that defense to overcome some attacker, and so it blocks some existing known attack. Except a slightly bigger, stronger attacker comes along and gets past it. And the instant reaction from the community is, well, okay, that defense is trash, so let's get rid of it and start over again. But that's not really how the real world works, right? In the real world, whether it's real people, real humans as they grow up, or even robotic systems, you sort of have a more of a reinforcement learning approach, where you fail and then you learn and then you iterate, right? And so in particular, for real world security systems, that's also sort of how things go, which is that, defenses are never going to be perfect. And nobody says, I'm going to, not use a firewall because it has known attacks that will eventually succeed, right? Generally speaking, people remember that, oftentimes the role of a security researcher or system is to basically raise the bar, raise the cost, whether it's compute or otherwise, for an attacker to win, so that, once the cost is high enough, they'll just go elsewhere or try something different. All right, so and another angle that's really sort of a complement to this is dealing with attacks after they happen, right? And so that's what, in particular, I want to talk about, which is how do we learn from attacks that actually do succeed? Because in real world systems, I think we're all sort of kidding ourselves if we say we're going to deploy a system and have it never, ever, ever fail, right? So turning that back around and connecting that feedback loop and saying, when attacks eventually do succeed, can we make use of that information and then provide better robustness for the system as a whole after an attack, right? So that's what sort of the digital forensics angle is all about. So let me give folks a little bit more insight into sort of what digital forensics typically means, right? So in general, let's say a network security context, what happens is, attacks happen. You hear about them all the time. Once they do happen, you call in an expert, whether it's Mandiant or FireEye or one of these companies that specialize in doing forensics, and you collect forensic evidence. You look at sort of logs and records of the attack, and you try to do this detective sort of style of analysis, try to understand how the attack happened and where it came from. And hopefully, if you're successful, you can actually trace it back to the attacker somehow. Perhaps it's not directly identity, but maybe it's the IP address or online accounts or something similar. And then, if you think about the benefits of something like forensics, it's actually quite interesting. It's twofold. One is you can understand where they came from, where the attacks came from. And in all likelihood, you're able to basically fix the attack and to sort of shut down the origin of the attack and mitigate it, right? And the other thing is that it actually serves as a nice deterrent for future attackers. So this is quite nice in the sense that attackers, even if they know that they can succeed, will think twice about performing an attack, knowing that there are forensic measures that will potentially, given sufficient time, trace the attack back to them and make them culpable for what they've done. Okay, so if we think about like forensics in the robustness for machine learning context, a natural place to start is data poisoning attacks, right? So what would this entail? So data poisoning attacks is where, for example, you take training data on the left side, and a poisoning attack basically involves adding some malicious data into the training data mix in such a way that the model itself, when it's trained on this data, has some natural corruption inside that's oftentimes hidden. And once it's actually deployed, an input can come along and basically be misclassified and produce the wrong result. Okay, so in this particular setting, what does forensic involve? You can imagine it would basically mean, once the attack has happened, you have a misclassification, and whoever is responsible for the forensic analysis can take that misclassification evidence and hopefully trace it back to what caused it. In this case, presumably the subset of malicious data that caused the training that corrupted the model that made this attack possible, right? And hopefully, if you can do that, then the next step would be to say, well, where did this training data actually come from? And you can, whether it's a corrupt data labeling service or someone, hacked into your file system and added the training data, whatever that may be, then further steps can be taken and hopefully lead you even closer to the attacker. All right, so that's sort of the setting for the first piece of work I want to talk about, which is forensics for data poisoning attacks for machine learning models. So how do we achieve this goal of once a poisoning attack has succeeded against your model, how do you go backwards and identify the training data that's actually made that possible? Okay, so I'll just dive right into it. I mean, the approach that at a very high level, what we're doing is we're basically isolating in this little example here, the little red triangles that represent corrupted, malicious training data, okay? And so the way that we do that is we cluster the training data. We somehow separate the training data into clusters, and then we iteratively remove clusters as we identify them to be innocent. In other words, we can confirm which clusters of training data do not have anything to do with this particular corruption or corrupted rule that somehow leaked into the model and made the attack possible, okay? And iteratively, as we identify clusters as benign, as innocent, whatever you want to call it, we mark them safe, and then you just repeat. And then you look at increasingly smaller remnants of the training data until no more clusters are prunable, at which time you presumably identified the training data, the corrupt training data, okay? So this is sort of an iterative algorithm, but it doesn't take too many iterations as you'll see, all right? So, you know, look at animation on the right side, this is what we're looking at. We're looking at, you know, taking the training data, isolating it and clustering it naturally, and I can delve into the details of that a little bit later on, into clusters based on how they affect the model, model's parameters. And then we basically do this sort of what if sort of hypothesis testing, if you will. We train versions of the model, new versions of the model with certain subsets of the data removed. So for example, if we're testing the cluster, the blue cluster on the right side, we're gonna basically train, sorry, this example is actually the opposite. If we're testing everything on the left side, we're gonna train a model with only the right side of the data, produce a model variant, and then using our evidence, which comes from the forensic attack, our forensic evidence, which comes from forensic analysis of the attack that succeeded, we test to see if that same evidence still triggers the misbehavior on model A, okay? And if it does, it means that whatever training set was still used to train model A still has the corrupted data inside, okay? And if it doesn't, that means that the training data set that we use is actually benign, okay? So in this case, we train two versions of these models, and when we test them, we find that model A is actually benign. And so that can lead us to conclude that the cluster on the right side is in fact free of corrupted training data, okay? And then we just repeat. So once we've identified that, then we say, well, let's look at the remaining data on the left side, cluster it, partition it. You know, usually there are natural partitions, and I'll discuss what that looks like later on. But then we repeat and you iterate, and you can identify more and more sort of benign clusters until there's a natural partition and you can't divide things anymore because both sides of both versions of the model look like they're corrupted. Okay, so at a very high level, that's what we're doing here. So this doesn't look particularly difficult, right? And so once you start thinking about like how you do this, well, you know, so this iteratively involves a lot of model training from scratch, right? Potentially what we're trying to do is we're saying every single step along the way when we're testing a new version of the model, one simple way to do this is to basically just say, well, we're just going to train it from scratch. Take that sample set of training data that we are testing, or both sample sets, and train a brand new model version from it. Except if you do this iteratively across a sort of a divide and conquer approach, this is going to train a lot of models, and obviously that doesn't scale. It's quite expensive. So we can do better, right? And obviously recently there's some very interesting work looking at model unlearning, where you take a trained model and you specifically teach the model to basically generate a version of itself that subtracts out the impact of certain training data. So unlearning can help, except the existing unlearning approaches are really focused on sort of privacy guarantees. So it's much more about, can you generate a version of your model that has no impact at all from this person's input for something like GDPR purposes, and guarantee that it has no such impact. So there are hard guarantees that really limit what you can do with this training data and the unlearning approach, right? So there's some really interesting work in the space, but because of the hardness of the guarantees, they really have to use some heavy-handed techniques. So they also don't quite work well for us because
the costs of these approaches are pretty expensive, and we can discuss that if folks are interested. So what we do is we do a approximation. So we propose this new thing that we call functional unlearning. And the idea is to basically approximate the version of a model that doesn't have a particular training set inside. All right. And the way that we do that is that on the left side, you see a standard sort of minimization, optimization function for just training a particular, a basic model. And what we're doing on the right side, we're basically saying, well, we are going to make the model optimize for getting a particular segment of the training data by basically forcing the model to train to a no knowledge label, if you will, a uniform probability vector when faced with inputs of from a particular region of the space. I don't know if that makes sense. It's kind of like training a version of the model through optimization so that it becomes really dumb with respect to a particular set of training data, right? And with the assumption that, if you never train with a particular set of training data, when faced with that training data, you perhaps give back a purely random or uniform probability vector. And we're trying to approximate that sort of behavior. And because it's an optimization function, this is actually fairly easy to compute. And instead of, training or even unlearning existing models, this becomes a very fast alternative. All right, so in particular, more specifically, this will reduce processing time for generating new variants of models from several hours, for example, to a matter of seconds. So it's actually quite significant in terms of time and compute savings. All right, so intuitively, I've sort of given you this idea of iteratively going through training input and sort of clustering the impact of some of these training data sets and testing it and seeing, which clusters, when you include them, produce this corrupted rule that's responsible for your attack. But why does this actually work? And the intuition behind why this actually works in practice is that when you look at poison data and normal training data, intuitively you can figure out and you can understand that poison data has to do a much more difficult task, right? Training data is sort of teaching the model that certain regions of the feature space mean certain things. And things should be reasonably consistent across most training data, right? Here's your face, here's that face, here's cat, here's dog, those kind of things. But poison data is different. Poison data is trying to get the model to learn something that is unusual. So a cat with this particular hat on actually is a dog. And so in doing, it has to create stronger connections further away in the feature space, right? And so that actually manifests itself if you look at sort of really dumbed down versions of what the feature space looks like. So if you take a two-dimensional PCA projection of training data for a bunch of these cases where you look at the corruption, the sort of corrupted bad training data versus normal training data, you'll see that even with really simple 2D visualizations, there's a significant distance in the feature space between benign data and the poison data. That's what we're showing here is that for a bunch of different environments, different injection settings, different types of applications, you can see that the benign training data and the poison training data are really quite far apart. And that's what makes actually the clustering really, really easy when you look at, we don't just cluster based on feature space. I won't get into the details of it today because I want to cover some of the other things, but it turns out that clustering using a number of techniques will work quite well. But there's more details about the actual clustering algorithm in the paper if folks are interested. So this separation, this natural separation between poison and benign training data is what makes this sort of divide and conquer algorithm fairly efficient. So let me show you some results. Again, there's a ton of more details in the paper, but we really try to cover all sorts of things, everything from face recognition to ImageNet to CFAR and different object classification. We look at different varieties of attacks, different ways of injecting poison backdoors, including a fairly recent attack we call physical backdoors that we had in CVPR 2021, right? So I guess almost 2 years ago now, that use physical objects that there's no current defense against. So different attacks, different classification tasks. And as our primary metric, we're looking at precision and recall. In other words, when you identify the subset of training data that you think is responsible for the poison attack, how precisely accurate is that set, right? Precision is, how much of the real ground truthing, precision is how much of your answer set is actually correct, and recall, of course, is how much of the ground truth did you include in your answer set, right? And so the results are just astoundingly good in the sense that they're all above 99%, with the exception of one, which is that physical backdoor training set. The recall is slightly lower. And if you think about why, it actually makes a lot of sense. It's in that this defense is able to detect training data that actually causes the attack. But what happens in the physical backdoors is that sometimes your images are ineffective at creating the attack association that you're trying to embed into the model. And so for attacks where you fail, where your training data is not very effective at creating that, this particular identification technique doesn't actually work that well. So the drop off of from 100% to 97% is what happens when certain portions of your training data that are trying to perform the attack are actually ineffective, and so it gets lost and ignored. Okay, so I want to cover some other things, and I'm also cognizant of time. So I'll quickly mention that this actually works as well on clean label poison attacks. And for those folks who are aware, clean label attacks are substantially different in the sense that you can't modify the label of your training data. So the corruption data has to be itself correct. You're limited in what you can control as the label of your training data. So you have to project a specific set of data into a far distant position in the feature space to try to affect something else. So the attack model it's actually a little bit different. And we're actually a little bit surprised that it still works really, really quite well on clean label attacks. Happy to discuss thoughts about why. We haven't delved to all the reasons yet, but it's actually slightly non-intuitive. All right, and briefly I'll mention, because in the security community, everybody loves countermeasures and adaptive attacks. And just to say that we actually did think of a bunch of different ways of countermeasures and trying to invent creative ways to defeat it. We haven't come up with anything that works really well, but we do explore quite a number of these countermeasures that try hard to get at this. There's more details in the paper. Okay. All right. So that was the sort of the, what happens with forensics when you apply it to poison attacks, right? And in the U6 paper, we actually show that you can go backwards using evidence of a successful attack and really fairly accurately get back to the training set that's actually responsible for that poison attack, right? So, but sort of the next question is, well, that's all well and good, but poison attacks are still just one portion of the adversarial landscape. What about adversarial examples, which are potentially much more prevalent and don't require as much work? All right, so we actually tackled this next in the CCS paper that we had just I guess a month and almost 2 months ago now, and so I can talk about that a little bit, and it's a little bit different, right? So if you think about the poison attack, going backwards and tracing your way towards the attacker is pretty intuitive. There's some data that is actually responsible for your attack succeeding, and so you just go backwards and find that data set, that subset of training data. In adversarial examples, it's not nearly that easy, and so what we've come up with is still an interesting way of using forensics, but it's a little bit different. So there's a little bit of a shifting gears moment here. So let's step back a little bit and talk about sort of adversarial examples and the strongest attack, which is white box attack. All right, so in a white box adversarial attack, the assumption is somehow the attacker has gotten full access to your model, right? Including parameters, architecture, everything. And this is really viewed as sort of typically the strongest threat model that you can have.
And, as I sort of talked about briefly in the beginning, there's no good solutions to this. Adversarial training can help a little bit. There's some versions of certified robustness, but it really has its own issues. So what can we do in this front? One question you can ask is sort of, are white box attacks realistic? And what does it take to perform a white box attack, right? And so you imagine, whether it's at Meta or Google or thousands or OpenAI, so many of these large-scale neural network services are being deployed in data centers. And one big question is, what about server breaches? And server breaches are something that we sort of have, I guess in the last few years, almost become numb to, right? When it used to be news when a company got breached and their data was stolen, but now we just sort of get used to it. We expect our data to eventually be breached and to be out on the black market. So in this sort of new world, if you will, what does this mean for neural networks? It's not great because what it means is that white box attacks are actually almost inevitable if you take the server breach perspective, right? So you take a facial verification or identification model, you train it, you do lots of work to train it, you deploy it, and sooner or later, right, someone hacks into your server, and perhaps increasingly so, these models are becoming increasingly valuable because how hard it is to train them, the amount of compute and GPUs and time and data labeling that goes into building one of these models. And if I breach your servers, and I can steal the model, and I can really do quite a bit, because now I can basically say, I can generate white box adversary examples forever and ever. And your model is basically, always going to be vulnerable. And yes, you can apply defenses, but as we've shown in the past through literature search, every single defense, it's only a matter of time, usually not much time, before someone comes up with a workaround. So what do you do? If you're a model owner and someone who spent a lot of time for this mission critical model, what do you do? Do you retrain a model? Turns out that's not great because attacks tend to transfer across models, particularly those using the same training data, right? And so what do you do? Well, one solution obviously is to basically say, we're going to retire these models and then restart from anew. And that's not great. That's really sort of the worst case scenario, because if you think about what these models cost, right? Some of these models cost millions now to produce, but not only just money, but also amount of time and human effort, right? There are medical models that take millions of dollars to produce. Some of them take, there's one data set apparently took 20 years to collect from 2 medical sites because the images were so rare and had to be human curated that 10,000 images took actually 20 years to collect. So you think about these kind of models that are so difficult to generate, and if the owner gets a server breach, the value of that model to them is almost nil, because it means that they are always going to be vulnerable to an adversarial attack. So what can you do? And not only that, but in some cases, you even can't retire models because some of these training data is specific to operations right now, right? So you can say, I will give up certain functionality, but for companies like Uber that use this for driver verification, you can't lose that functionality. That's core to what you do. Right, so that's sort of the question that we think of in this context. And it turns out that forensics can actually help in a sort of roundabout way, which I'll describe. Right, so how do we fix this problem? And what we come up with is with a way of thinking about a breach recovery system for machine learning models. Okay, to even when the attacker has your model and stole it off of your servers, what can you do to restore the functionality of that model and make it not an open book for attackers? All right, so there's a few things here. One is, of course, we still want to maintain the normal high benign performance of the DNN service, just like it was before the breach, okay? But also, more importantly, in addition to that, we want to be able to stop attacks that are generated using the breached version of the model. So at a particular date, we found out that someone's broke into our server and stole a model. We want to make sure that you are not able, the attacker is unable to use that model to attack the runtime servers that we rely on. Okay, so the question is, how do you do that? And the answer is sort of, we generate a new variant of the breach model, right? And this is the interesting part, where that, we're not necessarily saying we're going to break transferability. In other words, attacks that are generated using the old breach version of the model will still potentially work on the new model. But what we're going to say is that we're going to be able to augment the new version of the model with an attack detector that is specifically geared towards detecting attacks that come from the breach version of the model. Right, so if that makes sense, right? So you have a model, you lose it because, server breaches are just a thing. But once you notice that it's been breached, you're able to take that model, generate an attack detector for that specific variant while generating a new version of it. The new version runs alongside a sidecar that basically says, I know how to detect attacks that are generated using prior versions of the model. Okay, so here's a sort of a more visual explanation of that, right? So time on the x-axis, you deploy some version of the model, initial deployment, and at some later on date, you use logs, you use something else, you notice that, oh no, my server has been breached and version M1 of the model is now in the hands of the attacker. Okay, so you detect the breach, and there's a lot of work, existing work on breach detection for detecting these kind of things, right? So what you do is you take this early version of the model that has been breached, pipe it into our recovery system, and out comes two things. One is a new version of the model, we call M2 just for short, but also a detector for attacks that have been generated using M1. Okay, and both of these are going to now run in unison, and we're going to deploy these two together. And now it's going to basically run M2, but also be able to detect any unusual inputs that have been generated as attacks from using knowledge of M1. Okay, and at some point, let's say that you're unlucky, or your tech team is really falling down on the job, and there's another detector, there's another breach that happens again, and this time, of course, they get M1 and M2 and everything that you have, and you repeat the process. Okay, so now we're able to take M1 and M2, pipe it into the recovery system, generate a third version alongside a detector that detects both M1 and M2 attacks, and then repeat. Okay, and so you can actually see this iterating for a number of sequences, and hopefully this doesn't go on for too long, because then your servers keep getting breached, and that's really you've got other issues, right? Okay, so I guess the key question here, and I'll try to cover this, the core here, is how do we detect attacks, and how do we generate these new variants of models? So I have a few minutes left, and I want to get through sort of the intuition behind this, okay? And the idea here is that if you think about this super simple, intuitive view of what an adversarial example is, all right? You can think of it as sort of like little local minima in the classification surface that the attacker can detect because they have full access to the model. Okay, so let's say that here's a classification surface for M1, which has been breached. The attacker has full access to this. So the attacker can basically look at this and say, well, I can compute and optimize adversarial example because I have full view of this classification surface. So I can find that optimal local minima that will generate the best attack on the adversarial example. So our insight is that when you generate adversarial examples, they overfit, right? Because that's what optimizations do. They find you the best local minimum. They don't find you a mediocre local minimum. They find you the best one. They terminate when they can't run any further. So we can actually infer from that this particular local minimum is actually going to be less optimal on a similar but slightly different model, right? So that's where the model variant idea comes from. So if you think of this M2 then as a slightly shifted version of the classification surface, just like M1, but just a teeny bit different, then what happens to that same adversarial example that's been generated on M1 is that, well, it no longer is truly optimal, but it'll be perhaps okay. And the idea is that this sort of red dot still being below the X line, meaning that it's the attack still transfers and still succeeds in the attack, but it's no longer optimal, because you can imagine, the optimization function, if it had the blue line, going further and finding a true local minimum. So that's the key here, is that we're detecting the non-optimality of these potential adversarial inputs and using that to flag when a potential attack is coming, right? Because there is going to be a potentially large loss difference between the loss value of an adversarial example that's been generated on M1 when you apply that to M2, a slightly different version of the M model. Okay, and that loss difference is actually what we're using to detect a potential attack. Why? Because normal benign data, there's not that much of a loss difference. You can have versions of models that are very similar and, you know, very small differences in loss values for benign data. And intuitively, this makes sense. Empirically, it also sort of can be validated fairly easily. All right, so the next question is, how do we introduce this shift, this sort of very subtle shifting in the classification surface, so subtle, but yet producing a reasonably noticeable loss differential between M1 and M2. And the idea is fairly straightforward, but a little bit weird, which is that in order to generate M2, the next version of M1, what we do is we apply a training data augmentation technique, if you will. So we apply some hidden data to the training data set in order to generate M2. But the hidden data is interesting because the hidden data is actually comes from a unrelated data set. It comes from an unrelated task. So for example, if your model M1 and M2 are both for facial recognition, we'll take some sort of traffic sign recognition classification data set, which has nothing to do with the task that we're trying to train for M. But because it's orthogonal in nature, it shouldn't actually affect your benign accuracy, which is what we want. Training data that gets augmented, added into your training set, that doesn't affect your benign accuracy, but somehow just introduces enough of a random shift in the classification surface to produce the loss differential that we're looking for. Okay, so we call this technique hidden distributions. And I can answer questions about it, but probably almost out of time. So what I want to further comment is that over time, the more breaches that you are vulnerable to, let's say the attacker, you know, gets increasingly strong, M1, M2, it keeps on breaching your servers, and it has, like, let's say, multiple versions of your models, it can then over time start to compute better and better non-overfitting adversarial examples. Okay, and so the key metric for this approach is actually the number of breaches that you can still recover from before this overfitting detection technique no longer works. Okay, so that's our sort of new metric. And that's where I'll sort of sum up some of the results, and there's more results in the paper, but in general, the number of server breaches that we can recover from and still provide reliable robustness and benign classification tends to be in the high single digits. Okay, interestingly enough, the stronger the attack, the more robust the defense is, because there's more overfitting. The optimization function is better at overfitting. And so, for example, for Carlini Wagner, we can actually get close to 10, on average, 10 breaches are recoverable. Whereas PGD, some of the older schemes, you know, 7 or 8. As you know, these numbers are reasonably good in that if you get breached that many times, you probably really should, you know, a whole new infrastructure system. But, you know, still, those are some of the results. All right, so I'm almost out of time. So taking a step back, I'm sort of wrapping up. You know, one way that our work tries to get people to think about this perspective is that, you know, if you allow for scenarios where attacks do succeed because the attackers are persistent, they have tons of compute and other resources, you know, eventually they find a crack in your system. But using forensic evidence following the attack can actually dramatically change the balance of power, right? In both of these cases, we've shown how sort of knowledge of the breach or the attack can be used to really significantly enhance your system. Okay, and at a higher level, we want to sort of encourage the community to think about more realistic threat models beyond sort of the fairly binary versions that everyone seems to be focused on right now, right? From single snapshot models, we can look at sort of evolving models over time under fine tuning, whereas right now, most people are looking at binary success versus failures. We can consider things like partial compromises that slowly increase over time. And then, compared to just preventing attacks from succeeding, we can look at broader metrics like forensics and attribution of attacks and, gradual success rate of attackers over time with more and more. Okay, so I'll stop there. There's more information. We have web pages for these projects, but also more details on the papers on adaptive attacks, analytical results, details on algorithms for clustering, model generation, and so on. And source code is almost always on GitHub. But I'll stop there and be happy to take any questions.
Thanks, Dr. Ben Zhao, for the wonderful talk. So we have 6 questions that raised from the audience. The first question is from Jason. So he asked why uniform in the functional unlearning. He said, if I had left out the training examples in C, I doubt the learned model would have predicted uniform on them. It would have tried to generalize from the other training examples in D minus C. And he also have a comment, say there are other ways to try to approximate unlearning fast, such as the gradient-based method in a paper produced actually from Hopkins, from Suchi. So he put a link there. Maybe you can comment on that.
Yeah, that's a great question. Of course, right. So, uniform distribution is not truly random. It's not what you start with. And in the absence of a subset, you don't actually expect it to be, zero knowledge sort of uniform probability. But it's good as any simple way to target a version of that. So yeah, and I'm very happy to look at that archive link. Thanks for that. I think the short answer is really that, this doesn't have to be the only way to do this. There's multiple solutions to this, and all we need is any one fast solution, right? So, but I'll look at that and maybe that'll even speed things up some more. That's great. Thanks.
And maybe we group questions together. Another question also from Jason is that he said a $12 million cost to train GPT-3 probably included hyperparameter search. Once you have good hyperparameters, you might be able to keep them during retraining. Yeah,
so perhaps, again, I think the question is what type of retraining are you going to do, right? So if you retrain using the same training data to the point where you can actually reuse hyperparameters, which would be great, but chances are that, we're talking about the classification version of GPT-3, right? Not generation. Chances are that those classification results are going to basically transfer, right? So that's the challenge, is that if you want to retrain data and somehow have reasonably consistent and predictable robustness against adversarial examples generated using a prior version, you really have to do more than basic retraining. You have to intentionally, create some distance from the prior version. And even when you do that, I'm not sure I know of reliable work that predicts that type of distance in a reliable basis. Understanding transferability and breaking it is actually a pretty difficult open question.
Okay, thanks, Dr. Zhao. Then we have a question from Gautam. So he said that presumably the trigger for the poisoning attack is available post-compromise. Can't you just directly compare the trigger to the training data inputs?
Yeah, so you can do that, but sometimes it's not as simple as that. You can imagine, boy, there are so many papers that in the poisoning sort of attack arena, and many of them you can imagine all sorts of things. Some of these things are the training data is a warped version. It's not like a specific object trigger. Some of them can distribute the trigger into small different pieces. So for example, all the poisoning attacks on federated learning rely on this technique where you break segments of the trigger into little pieces, some of it along the feature space division line, some of them in the input space. So yeah, I don't think you can actually just directly compare. It will work for the most simple poison attack, yes, but there are a lot of easy workarounds that will make that quickly ineffective.
Thank you. And then we have a question from Adam. So he says, hello, Dr. Zhao. Could the adversary theoretically find out that the model unlearned the poison data and thus poisoning the whale with a different type of data that's creating a whack or mole type effect?
Yeah, absolutely. But that sort of defeats the purpose, right? Because remember, the point of forensics is that once we know where the data comes from, then we have knowledge that we can use to mitigate the attack, right? So for example, let's say that the attacker has, compromised, works or owns a data labeling service. And that's how they're getting the poison data into the pipeline. Because we can identify the subset of data that's corrupted, it's not to make sure that we can't ever be that they can't just change the data, right? It's not about that data per se, but it's about what we do with the knowledge of that data. So once we know, for example, that this particular data labeling service is the one that gave us the bad data, we can change providers. We can trace back to, who put that data set, into our service, for example. And in doing so, basically cut off the source of the injection into the data pipeline. And so that would prevent something like this, that, the attacker gets traced back. And even if we don't identify who they are and where they are, we know how they got into the system. We can patch that hole, making it far more difficult for them to reintroduce more poison data. They had to find another data labeling service. They had to find another server to breach or something like that and start from square zero.
Thanks. And then we have two questions from Kevin. So the first question is, have you tested functional unlearning against computer network attacks at the enterprise scale? Large networks often contain so much anomalous but ultimate benign data that complicates a model's ability to differentiate benign versus malicious.
Right. So I assume this is sort of talking about the poisoning forensics aspect. So no, I can't say that we have, but it's in many ways, if you think about sort of the idea here, is that it's unrelated to what we're trying to do, right? Because the premise of the work is that we have a successful attack and that we're tracing something back. So it's not to say that you can't generate false positives, which I think is the question is sort of asking. What happens when sort of weird input data creates false positives and things like that? But it's more in the sense that, we won't ever use it in a context without knowing that there's already been a successful attack. But I think if I take the question slightly differently, I think you're asking, can we take functional unlearning and adapt it to completely different environments outside of forensics context? The answer there is no, but that's an interesting question. At some point, perhaps it would be great for us to try that and see how sort of diverse we can use functional learning in other contexts, and there we might run into roadblocks. That's a good point. Thanks.
And then another question from Kevin is that he said security personnel often don't know when a breach occurred. Is this approach efficient enough to auto-generate detectors periodically in order to discover when a breach occurred? If you have a detector for, say, each week, then this could tell you the week when the breach occurred.
Yeah, that's a very interesting question. We did consider this sort of a preemptive, defense that kicks in whether your server's been breached or not. There's some variants here that you can think of. Yeah, you can do this. The challenge is that you can't keep generating model variants ad infinitum, right? So if you assume that this has failed after some number of repeated breaches, then it's no longer going to work. And if you keep regenerating new variants every week, let's say, then you're going to run out of new versions fairly quickly. So can you do it and recycle? Yeah, absolutely. I think you can. The challenge is, perhaps there's a version where you can sort of rotate through, let's say, 10 versions of these models. And when running one, always look for attacks generation using the other variants. You could try that. I think that's a viable way to deploy the strategy. I think there's some other trade-offs that we haven't thought through yet. But yeah, that's a very interesting approach.
Thanks. And then we have a question from Sona. And I think that it says, how would the proposed method handle cases when first trigger is changed by attacker, the second multiple triggers are used?
Right. So if I'll take the multiple triggers question first. Multiple triggers actually doesn't change anything, right? So at some point, there's going to be a single trigger that is required for this particular attack to work. So if that is true, then you'll be able to detect the training data responsible for that single trigger. And as for when you say triggers changed by the attacker, I'm not quite sure what you mean. I guess you mean like additional training data that has somehow evolved the trigger over time. But if you look at sort of the model at some snapshot in time, at some point, there's going to be a version of it, whether fine-tuned or not, that is corrupted based on a specific set of training data. And perhaps that training data comes through multiple iterations of training sets. And that may be what you're asking. I think that's an interesting question. There's probably ways to adapt the divide and conquer schemes to account for changing training data sets and fine-tuning over time. But that's something that we haven't looked into yet, but that's a very interesting question.
Thanks. My last question from Gautam again. He said that in a real-world setting, there may be millions of queries against the machine learning system per hour. Typically, a hard part of forensics is to recover system state at the time of compromise. What are your thoughts on what information to log or capture to assist with forensics? Do machine learning systems need to be modified to enable useful forensics auditing or logging? And he have apparently a great talk, by the way. Thank you.
Thanks, Gautam. That's really interesting. Yeah, we did ask ourselves this question, and I think the current version that is in the Usenix paper is sort of the first pass, which is assuming no prior logging information, no preemptive forensic logging and auditing. What can you do to recover? But I do think there's a more interesting question of like, what are things that you can do proactively to even further enhance the recovery process. And I would, we did think about this a little bit, but probably not enough. I think one simple answer is there are things that you can do to enable faster unlearning. And that, of course, depends on your version of unlearning scheme that you choose. Functional unlearning, like we already commented, is not the only way. And it's sort of a dumb approximation way of trying to approximate zero knowledge in the training set. But there are other ways that could be more specific and more powerful, and you can preemptively do things like checkpointing with models, albeit more subtle and smarter ways of doing that to simplify and to speed up that type of forensic backtracking, if you will, of the unlearning type. Yeah, thanks for that question. That's a good question.
So that concludes the seminar. So we look forward to see you next month for another seminar. And Dr. Zhao, we have a debrief in another Zoom link. See you soon.
Hey, thanks.
Mm-hmm.